Okay, good. Okay. Thank you everybody for joining us tonight. And also maybe in your time zone, it's morning or afternoon. So good morning, good afternoon, everybody. Welcome to perhaps the last Rising Star seminar of this academic year, right? And it's our great pleasure to have Kim with us. Kim is a postdoc researcher with joint affiliations at Arizona State University, the University of Melbourne, and Imperial College London. Kim received his PhD in electrical engineering from KTH in 2024, and his research interests lie at the intersection of game, decision theories, and large-scale systems with a focus on networking and security applications. Among all the recognitions Kim received, some highlights are that Kim got the Best Paper Award at IEEE Norms in 2022, and he is the recipient of the prestigious VR Postdoctoral Fellowship in 2025. So without further ado, I present Kim to you. Thank you. Kim,
Thank
please.
you very much, Tao, for the introduction, and welcome everyone to this presentation, which will be about learning-based control of network systems. So network systems are characterized by being very complex, dynamic, and distributed. And these properties introduce certain requirements for operation and management. First of all, we require automation in order to cope with the complexity. Secondly, we require control in order to adapt the system to dynamic events. And third, we require coordination in order to synchronize many distributed components. And these three requirements have sort of driven a fundamental change in network systems over the past decade to become fully programmable systems at every layer of the implementation. So for example, at the infrastructure layer, we can program the hardware configuration using virtualization. At the networking layer, we can program the forwarding decisions on the data plane, as well as the high-level policies on the control plane. And finally, on the application layer, we can program the execution and orchestration of services. And this programmability of the entire system means that in principle, we can specify a high-level objective or intent for how we want the system to operate, and then systematically compile that down into programmatic actions on the different layers for achieving the objective. However, how to actually implement this type of autonomous management in practice is still an open research problem. And in fact, this has been an active area of research for the last 30 years, where many different paradigms for autonomous management have been proposed and developed, some of which have even been standardized by industry. But if you go out in industry today and say you go to a cloud provider or a mobile operator or an enterprise, and you look at how they are managing their network systems, you will see that they have a much higher level of automation than what we had in the 90s and in the 2000s. But they are still quite far away from this vision of autonomous management. And this is exactly where I believe that my research will have an impact. So in my research, I focus on four broad areas, all of which are kind of centered around this vision of autonomous management, where the first area is about systems modeling, where I try to find better ways to model network systems in order to understand their operation on a fundamental level. The second area is about measurement and analysis, where I use empirical studies and evaluations in order to validate mathematical models and theories. And the third area is about optimization and learning of management functions in order to improve the operation of the system. And the final area is about systems engineering, where I try to design and develop platforms for supporting this kind of research. And these four areas are all interconnected in a general methodology that I advocate for, which can be understood on a very high level through this picture here. So in the middle, you have the network system that we want to operate or manage according to some objective. And the first step of this methodology is to identify a formal model of the system. And that model then serves two purposes. First of all, it allows us to analyze properties of the system mathematically. And secondly, it provides the basis for numerical optimization of control strategies, which is the second step of the methodology. So for example, if the formal model is a dynamical system, then we can optimize control strategies using reinforcement learning. And once we've optimized the control strategies, the final step of this methodology is to validate them on a digital twin, i.e. a virtual replica of the underlying system. And if that validation is deemed successful, we may also deploy the control strategy on the target system. So this is a very general methodology in the sense that it is not restricted to any particular type of formal model, any particular optimization method, or validation technique. And it can be instantiated with concepts from many diverse fields. So for example, when we construct the formal model, we can leverage tools from game theory, causality, automata, and logic. And similarly, when it comes to the numerical optimization, we have many different options, including convex optimization, reinforcement learning, and dynamic programming. So in the rest of the talk, I will demonstrate how to instantiate the methodology with some of these concepts, and I will also show you how it can be applied to practical use cases. So this is the outline for the remainder. I will start by briefly discussing how we can think about autonomous management on a conceptual level as a control problem. And then I will demonstrate how we can address that problem using my methodology in three different ways. First, I will instantiate the methodology with techniques from causality and use it to learn safe regions in a radio access network. Secondly, I will instantiate the methodology with concepts from game theory and use it to learn security strategies for an IT infrastructure. And finally, I will show you how we can combine the methodology with foundation models for incident response in the cloud. And lastly, I will conclude and present some takeaways. So conceptually, we can think about autonomous management as a control problem where the network system has an internal state that describes the current operating conditions. And during execution of the system, we are monitoring various properties like the service quality, the security, and the compliance. And through this monitoring, we obtain a lot of observations in real time, which are input to a control strategy mu that prescribes actions or inputs to the system for meeting a particular objective. So essentially, we are reducing the autonomous management problem to the problem of designing this control strategy mu. And while this appears on a conceptual level to be a classical control problem, it has some unique characteristics that makes it very challenging to address in practice. And the first challenge is just the sheer scale of the problem. So network systems typically have combinatorial control, state, and observation spaces, which grow exponentially in size with the number of system components. And this means that just from a purely computational point of view, this is a very challenging problem to address. The second major challenge is identification. So unlike many control systems, network systems do not have any predefined equations that govern their execution. And therefore, their dynamics have to be learned from operational data. Formally, there is some operating region within which the system is intended to function. And the identification problem is that we want to estimate a model that can describe the operation of the system across the entire region. But this is complicated by the fact that if you only observe your system while it executes, you will typically only get observations from a very small subset of the operating region. And that is generally not sufficient to estimate an accurate model. So to obtain an accurate model, you also need to explore edge cases and unusual operating conditions. And the final challenge is the operational deployment of control strategies. So network systems are subject to many constraints. We have constraints related to security, privacy, service quality, etc. And one way to think about this is that there is some subset of your operating region where all of the constraints are satisfied. And I refer to this here as a safe region. And we want to keep our system within that region as much as possible. But this is complicated by the fact that over time, the system is also going to keep changing, and even the safe region is going to change. Maybe because we roll out new software, or because there is a cyber attack, or we change the configuration. So we also need some way to very rapidly adapt the system to such changes to keep it inside the safe region. So in summary, the key challenges, in my opinion, are scalability, identification, and operational deployment. And in the next part of the talk, I will show you how we can address all of these challenges when applying the methodology to certain use cases. And the first use case is about learning safe regions in a radio access network. So this use case is motivated by an industry collaboration that we have together with Telstra. So Telstra operates a large mobile network with around 12,000 sites across Australia. And each of these sites uses Ericsson's equipment and hardware, which has tons of different parameters that you can tune in order to optimize the network. However, currently, most of these parameters are static, and they have been optimized or configured based on simple heuristics. So there is potentially a big opportunity here to optimize these parameters in a more principled way, and also to adapt them online to changes in the operating conditions. So if we zoom in on one of the 12,000 dots on the map here, it looks something like this, where for each site you have a number of sectors. So these sectors correspond to these white antenna arrays here. So in this particular site, we have 3 sectors, but Tesla also have some sites with only 1 sector, some with 2, 3, 4, 5, even 6 in some cases. And these sectors are then connected to the radio access network, which then connects you to the core network, and the core then connects you to the data network. And the use case that we focus on here is that we want to optimize a control strategy for dynamically allocating resources in the network based on demand. So for example, if the load of the network is very high, then we want to scale up capacity in order to accommodate that load. Whereas if the load of the network is very low, then we want to scale down in order to save on power consumption and costs. However, doing this kind of dynamic optimization in a production network is quite challenging because Telstra, of course, have agreements with many of their customers about the service quality. And we don't know if we go in and change the resource allocation, will that violate any of those agreements? So before we can do any kind of optimization here, we first have to identify a model that can give us a set of resource allocations that are safe with respect to the constraints. And once we have that safe region, then we can do optimization to find the optimal point within that region. And we have designed a method for doing exactly this, which consists of 4 main steps. The first step is that we use all of our domain knowledge about the network and the architecture and the configuration that Telstra is giving us, and we encode all of that information in a causal graph. Then we use the causal graph to infer an initial safe region without making any changes to the system, just purely inference. And once we have the initial safe region, then we gradually explore new resource allocations through a sequence of interventions on the system. So for each intervention, we change the resource allocation in the network, and then we measure and see what is the impact on the constraints. And based on the outcomes of those interventions, we then sequentially update our estimate of the safe region using Gaussian process regression. And these 4 steps can be understood in a very simple way through this diagram here. So the red area is the unknown safe region, and the red dot in the middle is our current operating point. So we know that the current operating point is safe because it satisfies all of the constraints. And the first step of the methodology then, as I mentioned, is that we infer an initial safe region using causal inference without making any changes to the system. And this typically gives us a very small subset around the current operating point, because the vast majority of causal effects cannot be inferred without changing the system. So for that reason, once we have the initial safe region, then we gradually expand it through a sequence of interventions. And when we select these interventions, we are balancing two conflicting objectives. So on the one hand, we want to learn as much as we can and as quickly as we can about the safe region. But on the other hand, we also want to maintain safety. And our method allows you to balance these two conflicting objectives in a principled way through a parameter that we call alpha. So the mobile operator can specify this parameter alpha, and then our method will ensure that the estimated safe region will be a subset of the true safe region with probability at least alpha. So this allows you, essentially gives you a tool for trading off learning efficiency against cost. So if you have a very high value of alpha, you're very safe, but you restrict the interventions that you can do, and that may lead to slower learning. Whereas if you have a low value of alpha, you can potentially learn much faster, but you may occasionally violate constraints. Now, to go into a little bit more mathematical and technical details of this method, I will use the following radio access network as an illustrative example. So this network has only 4 sites instead of 12,000. And each of these sites follows a distributed deployment where you have a radio unit that is close to the tower that is then connected to a distributed unit that typically runs in an edge cloud. And the distributed unit connects you to the centralized unit, which then connects you to the core network. And the first step of our method then to identify a model of the safe region of this network is that we take all of the information about the architecture here and we encode that in a causal graph. So each node in this graph corresponds to a system variable, and each arrow represents a causal dependency. So the left box here represents the causal structure of a distributed unit in the network, and the right box represents the causal structure of a centralized unit. So in reality, the graph is much larger than this, but this is just a compact way to illustrate it. And from this causal graph, we can make a few basic observations. So for example, if we have a constraint on the uplink throughput in the network, then we can directly conclude from the graph that all of the resource allocations on the centralized unit are going to be safe because there's no directed path from these variables to that variable in the graph. And therefore, there is no causal effect. So as a consequence, if we change these resource allocations, they cannot feasibly violate any constraint. Similarly, if we have a constraint on the jitter in the network, so maybe we want to keep the jitter low, we can conclude from the graph that resource allocations on the distributed unit can potentially have a causal effect on jitter because there are paths in the graph here. But we don't know the magnitude of that causal effect, so this is something that we have to learn from data. And mathematically, the way you should think about the causal graph is that it defines a bunch of conditional independence relations between your variables. And in particular, it encodes the fact that each node in the graph is conditionally independent of the ancestors if you condition on the parents. And the nice thing about this type of model is that it's very honest in the sense that you can directly validate the model against your data. And that's exactly what I've done. So I've taken each of the conditional independence relations in the graph, and then I formulate a statistical test where the null hypothesis is that the independence relation holds. So in the bar plot here on the x-axis, you have the different conditional independence relations, and on the y-axis, you have the p-values. And typically we say that if the p-value is above 0.05, we cannot reject the null hypothesis, and then we say that the independence holds. which clearly is the case in my experiments, as you can see. And now, once we have validated the causal graph, we can now use that to infer changes to the system without actually having to carry out those changes. And we do that using a mathematical framework called the do calculus. So the do calculus is just a very minor, simple extension to probability calculus, where we add a single new operation called the do operation. So this expression here is the causal effect on the variable capital P if you intervene on the system and you change the variable capital C to the value of lowercase c. And importantly, this causal effect is not necessarily the same as the conditional probability. They can be the same in some cases, but in general, they are not. And in addition to just being able to mathematically define the causal effect, the do calculus also allows us to derive estimands for estimating it. So given the causal graph that I showed you a couple of slides ago, and given the axioms of do calculus, I obtain the following derivations. And the details here is not important. I just want to highlight one thing, and that is that in my first expression here, I have a do operation. So to evaluate that expression, I have to actually change the system and see what happens. But in my final expression, I've essentially been able to marginalize out the do operation. And this means that I can use the final expression here to infer or estimate the causal effect without making any change to the system. All I need to do is that I need to learn these conditional probabilities here, which can be estimated from observational data. And this is, of course, very appealing for our use case, because whenever we have to go in and change the system, that involves cost and a risk of violating constraints. Unfortunately, we cannot always do this kind of inference. In some cases, you can prove that it's mathematically infeasible to infer the causal effect without changing the system. So here are some causal effects that I've estimated from our testbed. So on the y-axis, you have the CPU allocation, and on the x-axis, you have the CPU allocation, and on the y-axis, you have two different KPIs. And the curves here indicate the estimated causal effects with Gaussian processes, where the shaded regions indicate uncertainty. So what you can see is that there is a region on the x-axis between like 0.5 and 1.2, where we can reliably estimate the causal effects. But when you go outside of that region, we have a lot of uncertainty. And that is because outside of that region, the causal effects are actually not identifiable from the data that we have. So that means that the only way that we can figure out what is the power consumption going to be in the network if we set the CPU allocation, for example, to be 2.5, is to actually go in, do that change to the system and see what happens. So that's exactly what we do then in the second phase of the method, where we conduct these kind of interventions in order to learn more about the safe region and about the causal effects. And when we select these interventions, we don't do it randomly, but we do it according to a particular intervention policy, which is defined here in equation 1. And before I explain the equation, let me just start by giving you the intuition. And the intuition here is that we want to intervene sort of at the boundary of our current estimate of the safe region. Because at the boundary, we believe that we will be safe, but we're also going to get a lot of information about the neighboring points, which hopefully will allow us to refine the boundary and expand it. And the way I express this mathematically is through this equation here, where pi is my intervention policy, S is the estimated safe region, and then I have a maximization where I pick the intervention within my current estimate of the safe region that has the maximal uncertainty as encoded by the numerator divided by the cost of the intervention as encoded by the denominator. So essentially, this is a very simple, greedy intervention policy that balances safety, exploration, and cost. And in this figure here, you can see how the policy selects interventions over time, as indicated by the crosses here. And you can also see the evolution of the estimated safe region in the blue area. So if you start looking at the top left corner, you can see that we start out with a very small estimate of the safe region that we infer. And then gradually, as we're conducting interventions, we are learning more and more about the safe region. And after about 15 interventions, we have a pretty decent coverage. And you can also note that most of the interventions that we conduct are actually safe, but not all of them. But this can be controlled by tuning this parameter alpha. So in this example, the estimated safe region, the red area, is unknown, but it's static, it doesn't change. But we know that in practice, in operation, the network keeps changing over time. I mean, you have changing load patterns and changing configurations. So I've redone the experiment with a dynamic safe region, and then I obtained the following results. So in this case, it's much more tricky to learn the safe region because you're essentially chasing a moving target, which means that even if an intervention was safe in the past, it's not guaranteed to be safe now. And that makes it much more difficult to learn the safe region, and it's also reflected in the results, where you can see that the blue area is much smaller in this case. But still, after around 15 interventions, I would say that we have a pretty decent estimate of the safe region. So the method still works even if you have a dynamic safe region, but in this case, you have no theoretical guarantees, obviously, since you're chasing a moving target. And these two experiments have been for safe regions that are two-dimensional and have a nice connected shape, just for illustration purposes. But they've also done a lot of experiments with more high-dimensional safe regions that are disconnected and have spiky shapes. And if you want to read about those results, they're available in the paper. They are also quite positive results, but they cannot be illustrated in a nice way due to the high dimension. So in summary, our method for identifying a safe region of a radio access network consists of the following steps. First, we use our domain knowledge and code that in a causal graph of the network. Then we validate the graph against our data, and we use it to infer an initial safe region using causal inference. And then we gradually expand the initial safe region through a sequence of interventions. And based on the outcomes of those interventions, we sequentially update our estimate of the safe region using Gaussian process regression. And this method gives us quite nice numerical results and also some theoretical guarantees, as you have seen. And now finally, when we have the safe region that we have estimated, we can do the optimization that we wanted to do from the beginning. And to be honest, the optimization now becomes rather straightforward, since we have a causal model of the safe region that can essentially be used as a simulator of the network. So it tells us for each resource allocation, what is the impact, the causal effect on all of the KPIs. And that means that we can apply standard numerical methods like reinforcement learning or dynamic programming. So in the particular experiment I've ran here, I've optimized a control strategy for minimizing the power consumption in the network while keeping the throughput above some threshold. And I applied 3 different methods for the optimization, 2 reinforcement learning methods and 1 dynamic programming method. And all 3 of them converged rather quickly, but the reinforcement learning methods converge to slightly lower cost values, so they perform better. And after optimizing these strategies, I then validate them on our testbed or digital twin. And here there are many ways you can do this validation in very sophisticated ways, but I've done a very simple validation here, where I just take the control strategy that I obtain at each point of the optimization here, and then I run it 5 times on my testbed for a fixed evaluation horizon, like 30 minutes. And then I run it 5 times in my model in the simulation for a corresponding evaluation horizon. And then I average the results and I compare. And that gives me these curves here, where the points are the mean values and the shaded regions are the standard deviation. So unfortunately, you can see that the two curves are not identical. So ideally, they will be basically on top of each other. But we are still quite encouraged by the fact that these two curves follow a similar structure, which indicates that what we are learning in the model is actually translating into real performance gains on the testbed. So in summary, we have now gone through all of the different steps of this methodology. So we started out by spending a lot of time identifying a causal model of the safe region. Then we used that for optimizing our control strategy using reinforcement learning, and then we validated it on a digital twin. And now finally, we would want to deploy the strategy in the production network. And this is something that we are currently work in progress together with Telstra, but we haven't had time to complete these results yet. So this was just one instantiation of the methodology. But to demonstrate the generality of this methodology, in the next part of the talk, I will show you how we can instantiate it in a completely different way based on game theory and also apply it to a different use case. Any
Question.
question, Tom?
Yes,
Yeah.
that's the question time. Sorry, I will be quick. So first,
Yeah.
I want to go to the chat where Sandip raised a question at the beginning of your causal learning part. So I guess his question is, what are the assumptions that you're imposing when you collect data for the causal learning? And do you assume that underlying system is stable, is safe, is like, attack-free setting?
Yeah, that's a very good point. So the only assumption we make, so we don't make any assumption about like IID samples or anything like that. We only assume that the samples are drawn from the system from basically a generative model that is consistent with this causal graph that we have modeled. So we require that the causal graph has to be correct with respect to the underlying system. That's what we require of the data. That's the first requirement. The other requirement is that when we go in and intervene on the system, so we change the resource allocation, then we need to we need to control the other variables that are related to the variable that we are changing in order to really measure the causal effect. So there is a certain cost related to doing the intervention because you really have to control certain variables in the network, which can be non-trivial in some cases. But those are the only assumption I believe that we make for the data collection.
I see. Kim, I have a quick follow-up on the modeling part. So do you consider your system as a closed RAN or open RAN where the user demand and also how the connection pattern is going to change over time? It's basically a dynamic setting.
Yeah, that's a very good point. So we assume that it's a dynamic setting where things are changing over time. So in this graph here, for example, you can see that we have a subscript of t on all the
Hmm.
variables. So LT minus 1, that's an impact on the variable value at time t. And essentially, after discussions with Telstra, our understanding is that the whole network is moving all the time. They actually have increasing number of users every month. So everything is kind of moving. So we basically are trying to track a moving system all the time in our learning.
I see. Then when you do the boundary intervention, sorry, yeah, the intervention, I recall that you mentioned that when you are dealing with dynamic settings, your intervention is less guaranteed or something does not hold anymore, so that you are actually possibly getting into the danger zone out of the safe region. So what do you mean in that case by dynamics? Isn't this dynamics the same dynamic pattern you show in the causal graph, or actually you're talking about different dynamics thing?
No, that's true. So this is the same dynamics that I'm talking about there. So actually, this is a good point. Actually, when we specify the constraints,
Mm-hmm.
like the constraints or like the throughput in the network, we require that Telstra gives us some kind of time horizon that, okay, the
Oh, I
throughput
see.
on the network should be above like this level for the next 15 minutes. And then we
Mm,
can, when we do an intervention, we can then validate, okay, we do the intervention and check for the next 15 minutes, what was the impact on the constraints? Because
I see.
otherwise you may have to wait for forever, to validate if the constraint was validated or not. But
Mm,
now we assume that the constraints are actually for some limited time period, even though the system has an infinite horizon, but this constraints should be over a limited horizon.
limited. Okay, I see. Thanks. Thanks. Yes, please go on, Kim. Thank you.
Thank you. Very good questions. And yeah, so in the second part of the talk, I will instantiate the methodology in a completely different way based on game theory and apply it to a different use case, namely learning security strategies for an IT infrastructure. So here I consider a general IT infrastructure that consists of interconnected components that jointly provide services to a client population. And this infrastructure is operated by an organization, which I refer to as the defender. And the defender monitors the network and can also execute defensive actions. In addition, there's an attacker that seeks to intrude on the infrastructure and wants to compromise components. And to achieve this goal, the attacker uses reconnaissance to gather information and find vulnerabilities, and then it has to exploit those vulnerabilities in order to gain access. And I study this use case from the defender's point of view. So my goal here is to learn game theoretic security strategies for mitigating or responding to intrusions in real time. Now, a challenge in following a game theoretic approach is that the game theoretic model will never be a perfect fit of reality. So network systems are so complex that we cannot even hope to capture all of the details in a model. And this means that whatever model we are using, it will always have some degree of what we call model misspecification. And this part of the talk will be about how we can quantify and how we can manage this misspecification. In particular, we will propose a method for online learning of game theoretic security strategies where we don't require a perfect game model. We only require a conjecture about the model, and that conjecture can be updated over time, and it can also be misspecified. And this method consists of two main parts. First, we have Bayesian learning to update the conjecture based on feedback from the system. And secondly, we have rollout to compute the security strategy and adapt it to the conjectured model. So more specifically, at each time step of the game, each player will pick an action. So the defender will pick a defensive action, the attacker will pick an offensive action. After executing their actions, they will get some information feedback. For example, the outcome of a command or a security alert. And based on that feedback, they would then update their conjecture about the game model using Bayesian learning from a prior distribution. And we say that the player is misspecified if the prior assigns zero probability to the true model. And I would argue that that is always going to be the case in practice. The outcome of this Bayesian learning is then a posterior distribution over potential conjectures. And from that distribution, the player would then sample a particular conjectured model and use that to compute a new security strategy using rollouts. And this rollout computation works as follows. So we take the conjectured model, and then we simply roll that forward in time a few time steps by predicting the outcomes of actions and costs. So outcomes in terms of the next state or belief state. And then we simply pick the action that, according to our lookalike predictions, leads to the minimal cost. And this way of computing the security strategy is scalable in the sense that we can control the computational complexity by controlling the depth of this look-ahead tree. And it's also a principled way to compute a security strategy in the sense that it can give us certain theoretical guarantees. In particular, we can show that the rollout computation will never degrade the performance of the strategy under general conditions. And in many cases, it can also lead to a drastic performance improvement. And the second main result is that the Bayesian learning of the conjectures will converge to a set of conjectures that are consistent with the feedback. So mathematically, this means that the posterior distribution will assign all probability measure on those conjectures that are most likely to have generated the feedback that we observed asymptotically. So this convergence can be understood through this time series here, where on the x-axis you have the system model, on the y-axis you have the probability, the black curve is the conjecture distribution, and the shaded area here and the dashed lines are the set of consistent conjectures. And the dotted red line is the true model, which is unknown. And that happens to be equal to 1 in this case. It's just a scalar. So if you start looking at the top left corner, you can see that the player, in this case, has a uniform prior between 0 and 0.8. So clearly, the player in this case is misspecified because it assigns 0 probability measure to the actual model. And then over time, as we're doing conjectural learning, the conjecture distribution is moving closer and closer to the dashed black line, which is the set of consistent conjectures. And it just happens to be the case in this simple example that the set of consistent conjectures is actually a singleton set, and is also closest in the Euclidean distance to the true model. But that does not have to be the case in general. And this type of convergence can give rise to a very interesting form of game theoretic equilibrium, which we call the Burke-Nash equilibrium. So in this equilibrium, each player will play the game optimally according to their own conjecture about the model and according to their own computational constraints. So this can give rise to quite interesting situations where the attacker and the defender have completely different perceptions of the game. Maybe the attacker is aware of some vulnerabilities that the defender is unaware of, and the defender is aware of some system properties that the attacker is unaware of. But despite these misconceptions, they still play the game according to some form of mathematical equilibrium. And I would argue that this type of equilibrium is much more suitable for cybersecurity than the classical Nash equilibrium, which require that both players have the same exact model of the game, and also that they don't have any computational constraints. And we prove in our paper that if our method converges, it converges to an equilibrium of this type. So if you're interested in the more theoretical details and also lots of experimental validation of this theory, you can find that in the paper. So the main takeaway here is that this game theoretic model or method, by relaxing some of the classical game theoretic assumptions, we obtain a practical method for online learning of game theoretic security strategies. And this works very well when you have a narrowly scoped problem with a well-defined action space. But it's not clear how you would apply this game theoretic approach to a more open-ended security problem, where you have kind of a fluid action space. So in the final part of the talk, I will briefly discuss how we can address these more open-ended problems by combining the methodology with foundation models and large language models in particular. So here I consider a scenario where a security operations center has received alerts that indicate potentially an ongoing incident in the system. So the task here is that we need to investigate the incident and we need to generate a plan of action. And this is a very open-ended problem because when you investigate a security incident, your actions essentially have to be tailored uniquely to each particular incident. And it's very hard to predefine the action space in this case. So to address this type of open-ended problems, we have developed a multi-agent incident response system that consists of several agents that collaborate to investigate an incident and generate an optimized response plan. So each agent here is an autonomous software process that has an internal state and some logic for execution. And the agent also has access to a large language model that it can use for processing inputs and generating outputs. Moreover, it can execute or invoke different tools. It can, for example, run commands in a digital twin. It can run code in a Python sandbox, and it can fetch information from external APIs. And when we design the architecture of this system, so when we design the roles of different agents and how they interact, we follow three main design principles. The first principle is verification. So to mitigate the unreliability of large language models, we always validate the output generated by an LLM. In some cases, it can be validated directly on the digital twin. In other cases, it can be validated through an external API. And in some cases, it can be validated by another agent. The second principle is to leverage external tools for planning. So despite the remarkable capabilities of large language models, they are still quite ineffective and inefficient when it comes to planning over longer time horizons. So for that reason, whenever we have a decision-making problem, a sequential decision-making problem in the system, we instruct the agents to generate a code model of the decision process. And then we use that code model for doing planning with traditional methods. And that allows us to do planning over longer horizons very efficiently. And finally, the last principle is decomposition. So large language models tend to work best when you don't have too much context. The sweet spot is around a few 100,000 tokens. So for that reason, whenever we have a very complicated problem with lots of context, maybe lots of log files, then we decompose that into sub-problems that can be managed by individual agents in parallel. So based on these three principles, we propose the following architecture for a multi-agent incident response system. So this is a hierarchical architecture that consists of 13 different types of agents that are organized in a tree. At the root of the tree, you have an orchestrator agent that manages the overall process and delegates work to sub-agents. And then you have many different types of sub-agents that are tailored for different types of problems. So we have one set of agents for investigating the incident and generating a report, another set of agents for validating the report on the digital twin. And once we have validated the report, there is then input to another set of agents for generating a code model of the response process. And that code model is then used for planning. And finally, the generated plan is then validated by another set of agents. So all of these verifier agents in the system, they implement sort of verification loops where you have a worker agent that generates an output, for example, an incident report, and then you have a verifier agent that validates it against, for example, the digital twin, and then outputs a verification score. And that score is then input to a control policy that decides whether we should continue revising the output or stop and accept the current version. So this verification loop here allows us to control both the efficiency of the system and the quality of the outputs. In particular, we can prove that for each verification loop, there exists an optimal control policy that has a threshold structure under general conditions. So whenever the verification score X exceeds some threshold alpha, that is when you should stop and accept the current version. And the benefit of this threshold structure is twofold. One, it means that we can very efficiently compute the control policies. And two, we can use this threshold alpha as a knob to control the quality of the outputs of the system. The only challenge here in the analysis is that this verification score X is actually generated by an agent. So it could be overestimating or underestimating the actual quality. So for that reason, we have to do a probabilistic analysis, and then we obtain the following result, which states that the system can guarantee a certain performance level with a certain confidence that can be controlled. And I think that this is quite a nice result because it means that even though we have a very complicated system with many unreliable large language models, the system as a whole is actually reliable and gives you certain performance guarantees based on your requirements. So this is still a little bit of ongoing work, so I don't have a paper to refer to here, but hopefully it will be available in a couple of months. And then, of course, there will be a lot of experimental evaluation in addition to the theoretical analysis here. So in conclusion, autonomous management of network systems has the potential to address many of the challenges that we currently see in industry related to cost efficiency of the operation, lack of human operators, and increasing volumes of cyber attacks. In this talk, I have advocated for a methodology that involves three steps: identification of a formal model, learning-based control, and validation of digital twin. And I've shown both theoretically and experimentally that this methodology is general, and it can be effectively applied to several different use cases. And while several challenges remain to fully operationalize this methodology, I believe that it provides a foundation for the next generation of network systems. Thank you very much for your attention.
Thank you, Kim. Thanks. So first, let me stop recording.